Hello and welcome back. In the last video, we learned how to add, subtract, and multiply inside the modulus. But we skipped one operation on purpose, division. Today we fix that. Why division is a problem? In normal math, dividing by a number is the same as multiplying by its reciprocal. Modular arithmetic has no fractions, so we need a whole number that acts like 1/2. On the left, 6 divided by 2 equals 3. In the middle, that's the same as 6 times 1/2. On the right, 6 times 1/2 in mod 7 doesn't exist. 1/2 isn't a whole number. We call this the modular inverse. A number x such that a multiplied by x leaves a remainder of exactly 1. A times x is congruent to 1, mod n. X is the number that undoes multiplying by a. Finding an inverse by brute force. Let's find the inverse of 3 mod 7. Try every number from 1 to 6. 3 times 1 is 3. Mod 7 is 3. 3 times 2 is 6. Mod 7 is 6. 3 times 3 is 9. Mod 7 is 2. 3 times 4 is 12. Mod 7 is 5. 3 times 5 is 15. Mod 7 is 1. Found it. So the inverse of 3 mod 7 is 5. Let's verify. 3 times 5 equals 15. Mod 7 equals 1. So 3 inverse is congruent to 5 mod 7. Why not every number has an inverse? Not every number has a modular inverse. Let's write to mod 6. 2 times 1 is 2. 2 times 2 is 4. 2 times 3 is 6. Mod 6 is 0. 2 times 4 is 8. Mod 6 is 2. 2 times 5 is 10. Mod 6 is 4. No x ever gives you 1. 2 has no inverse mod 6 because the greatest common divisor of 2 and 6 is 2, not 1. The rule: a has an inverse mod n only if greatest common divisor of a and n is 1, which is why ZK systems use a prime as the modulus. Fermat's little theorem. Brute force is slow for huge primes. Fermat's little theorem is the shortcut. A to the power of p minus 1 is congruent to 1 mod p, as long as p is prime and a is not a multiple of p. True for every number from 1 to p minus 1. Deriving the inverse formula. Split the exponent from Fermat's theorem to isolate the inverse. A to the p minus 1 is congruent to 1 mod p. Split the exponent. A times a to the p minus 2 is congruent to 1 mod p. Compare to the definition. A times x is congruent to 1 mod p. So a inverse is congruent to a to the power of p minus 2 mod p. Worked example using the formula. Let's check the formula against the answer we already know. A equals 3, p equals 7. 3 to the power of 5 mod 7. 3 to the 5th equals 243. 243 mod 7 equals 5. Matches the brute force answer. Why ZK needs this? Circom and every ZK circuit divide by multiplying by a modular inverse. There's no division operation inside a finite field. A divided by b mod p doesn't exist directly. Instead, we compute a times b inverse mod p. Every circum constraint that divides is really doing this underneath.